I want to talk about a project that I actually did a number of years ago, but which is an example, I believe, of how creationist research might actually work, how it contrasts with research outside of creationism. And in this particular case, just an example of, I think, a theory that works, a theory that's successful. Thus, it should be an example to people of how we ought to do research. It began many years ago when I was an undergraduate at the University of Chicago. I often heard the claim that fossil order is explained by evolution. I phrase in many different ways, but it can be something like fossils prove evolution or any one of a variety of forms. I contemplated this claim, which I heard multiple times, and thought about what it meant, especially since I was trained in paleontology and fossils. I was interested in the statement and its truth. A more precise way to phrase this particular statement is that organisms appear in the fossil record in the very same order that evolution suggests they should appear. In other words, evolution is a theory that, even though it can't do this in retrospect, it can actually develop a theory of the order that organisms actually appeared, and it can do that independently of the fossil record. You can do it from studying modern organisms and develop the likely evolutionary scheme that would have led to the organisms we see today. And then you can take that order and compare it with the fossil record. And the claim is that the order in the fossil record is, in fact, the same as evolution says it should be. I think it's part of my personality that I, from childhood, never really took what I was told at face value. I often tried to check it out, poked at it to determine how true it was. And this is an example of the very same thing. I heard the claim. I didn't accept the claim. I was intrigued by it. I wanted to test it. I really didn't have an opportunity to test the idea all the way through my formal education. I was a little busy with doing that. But in the summer following the receipt of my doctorate, I found myself in a little bit of a vacuum there. I didn't have any of my formal studies that I was committed to, and I hadn't yet started teaching at Bryan College, my first job there. And I had a couple months to do what I wanted to. Last time I was ever able to do that. The and I sat down and thought about 7 of the strongest arguments I thought existed for evolution, and I worked through each of those problems to determine a creationist response to it. One of those questions is this one: the claim that fossil record order is explained by evolution. Is that in fact true? Do organisms appear in the fossil record in the same order that evolution suggests? It was a very difficult project. It involved a lot of work. It took probably a month and a half of the 3 months that I had there to work through this one. This was the most difficult one to address, because it involved something that I don't think anyone has ever tried to do, which is to take all of the organisms that exist, bacteria all the way through humans, and based upon what we know about the biology of these organisms, determine what the most likely evolutionary tree looked like, and thus from that determine the order that these organisms should have appeared, without ever looking at the fossil record in the process. Don't let that bias, just based upon the modern biology, and then check that order against the actual fossil record. The result of that work that particular summer was that the vast majority of evolutionary lineages do not, in fact, correspond to the order that's found in the fossil record. Now, you have to realize if you have a single tree that starts at one point, goes to every single organism on the planet that exists in the present, each organism is on a lineage from that first point. And so one has to actually test each one of those lineages to determine how it fits with evolution. And unfortunately, since they're all coming from the same point and very often follow each other for quite a ways before they finally diverge, they're not independent tests, each one of the lineages. And so it's hard to do real statistics on it. But the best I could come up with was that roughly 95% of the lineages do not have an order in the predicted by evolution that corresponds to the fossil record. There were only a few groups that seem to have a correspondence between the fossil record order and the order that evolution predicted. In fact, a little less than 5%. Now, in science, we generally think that if a hypothesis can explain 95% of the data, who cares about the 5%? You just you go on. And so that's what I literally did that summer was I just discarded that 5% and went on. Except that one of those groups kind of nagged at me, and it was the group of the plants. It was the higher order groups of plants that seem to fit that order. It's part of the 5%. It's not a very large percentage of the fossil record, but it was intriguing the degree to which it corresponded. Now here is, and so what would happen is I would eventually come back to this, to the issue of the fossil record of the plants and examine this a little more closely. And that's what you see here. Here's the best phylogeny or theoretical evolutionary tree I was able to develop with the information that I had available, or that was available in paleobotany in 1989. So here we have the major groups of plants. Basically, the equivalent of the phyla of animals are the divisions of plants. Most of these are divisions of plants. Some are individual taxa, like is a single genus. But here's the best guess evolutionary tree for the fossil plants, or all plants, fossil and living, all put together. So we first have to determine what the evolutionary order is. And on a diagram like that, like this one, we can see that Horneophytopsida is the very first branch. So they should have a fossil record going back the earliest. Then we have the Aglaophyton and so on. Going up the sequence, we can then, for each of these organisms, determine the order in which they should appear in the fossil record. And we can then list those taxa and the predicted order. Some of these have the same number because they branch together at the same time, and so you cannot determine which is earlier or later. Then the second thing we need to do is to look at the fossil record, ignoring the claims of evolution. If we look at the fossil record as a stack of rocks from the bottom of the screen to the top of the screen, the oldest rocks don't have fossil plants at all. So the very first rocks way down there at the bottom have a few plants. The oldest rocks in the Devonian the upper Silurian have a few fragments of plants, few types of plants. The width of this green shape here is a measure of how many different plants are found at that level. So this is focusing on the Paleozoic portion of the fossil record of the plants. And you can see that the very oldest rocks with plants don't have very many. As you go up, the number of plants increases. It increases to a maximum, drops back down a little bit in the Mississippian, then increases pretty steadily through the upper Paleozoic. And you can break the total number of plants out into the various subgroups. And on here in this chart, and so, for example, way down at the bottom, the very first organism encountered there is a Horneophytopsida, an Aglaophyton. And so we're now going to look at where these diagrams, where they first appear at the lowest point in the fossil record. And so we give those numbers as well. Horneophytopsida 1, Zosterophyllopsida and Lycopsida come in next, and then Aglaophyton, Rhyniopsida, and so on. And we can go all the way up and compare that with the we got from evolution's prediction. We can actually do a correlation of these two, and it's really quite astounding. The R, not the R squared, but the R is 0.99. That's explaining 98% of the data is explained by a line between the two, suggesting that in fact the order of higher groups of plants is right exactly the way evolution would expect. This was something I observed a number of years earlier when I did it for all organisms. This group stood out as unusually enough in the order that evolution predicted. Pretty astonishing, actually. Okay, now at this point, an evolutionist would have a party. It's like, yeah, that's exactly what I expected. Now here is where things would diverge when you come to a creationist. A creationist is going to say, now wait a minute, I can't accept that explanation. As beautiful as the explanation seems to be, as good as evolution seems to be at explaining the order, I don't think it's true. I don't think evolution is true. From the Bible, I deduce that evolution, there isn't enough time for evolution, and that God created the plants and different groups of plants, the created kind of plants, created specially, independently, poof, on one single day. So there should be no order in the fossil record that corresponds to an evolution, because an evolution never occurred. So I have to look at the same data and pause and say, perhaps there's another explanation. I need to find another cause for this order. And thinking back at my classes in paleontology and even my very first class in paleobotany, I remembered a claim that was made, sort of a theme, a thematic tie throughout the course, that the evolution of the plants can be understood to be an evolution from the sea to the land. Very much analogous to the claim that's made in the vertebrates, that the vertebrates evolved from the ocean onto the land. It was also the claim of, in fact, paleobotany, that the oldest plants, in the broadest sense of the word, would be the photosynthetic bacteria in the Precambrian. Then we have algae that came after that, and then we finally have land plants after that. That's a sequence from the land, from the ocean onto the land. And so it was with this thought in mind, I wondered if I could rethink the evolutionary sequence as perhaps an ecological sequence. Is it possible that that plants were at one point in time arranged ecologically in a non-random order, in an order that makes sense, that they were designed in such a way that there were plants designed for the ocean, plants designed for the shoreline, plants designed for moving further inland, that in fact there was an ecological zonation of plants running from the ocean onto the land, maybe from the lowlands to the highlands of the land, and that ecology, ecological sequence might have been picked up by, for example, the flood and picked off in that same kind of order. And maybe that could explain the order of the plants in the fossil record. So, to test that hypothesis, I went back and created another evolutionary tree, another phylogeny. I took out all of the characters, traits of the plants that had nothing to do with living independently of water or living in dry environments. I it's I basically looked for characters that could measure the relative position of a plant with respect to a source of water. So, for example, in some of these plants, the sperm is released and swims in the water to the egg. Well, that requires standing water. In contrast, you go all the way to something like a corn plant, and the pollen grain of from corn lands in a dry environment on the silk, grows a tube up the silk and down to the uh, to the to the egg, and then the sperm goes through that tube to the egg. So you have a situation where you can have this is a dry environment. So corn is basically designed to exist without standing water. That could logically be something that's standing farther away from the water from something that depends upon it. So in taking characters between and taking out characters that had nothing to do with their ecological position of water versus land, I created another, if you wish, evolutionary tree, or it's an ecology tree. Now, let's back up. I just showed you the previous slide was an evolutionary sequence. That's that one. The ecology sequence is this one. Back to evolution to ecology. Astonishingly similar. The order is very much similar. So it sort of confirms the evolutionary claim that if evolution did occur, it seems to have been an evolution from the sea onto the land. So now let's take that ecology diagram and determine the order of first appearance of things based upon that. When we do that, when we do another correlation, we find basically the same correlation, a little bit, just a teeny bit better. So it appears that plant groups in the fossil record appear in both an evolutionary order and an ecological order. So we have potentially an alternate explanation. But the question then becomes, what if so one can envision it. So that I began to think in terms of these basic divisions of plants arranged ecologically. What is a reasonable model, a viewpoint, a perspective on biology that would lay these plants out in the predicted order, that they would be living in that kind of order? And I couldn't help but come to think about quaking bogs. And that's because I grew up in Northern Illinois. Uh, and many of you are perhaps living south of there, and so you have no experience with quaking bogs. Quaking bogs are primarily a phenomenon of the glaciated terrain to the north. But I had an experience early on in my childhood, 12, 14, somewhere around in there, where I had an experience on a quaking bog, and it was ingrained in my head. It was a wonderful thing. Let me explain what a quaking bog is to start with. The theory on how they form is that there was a lake formed. Usually, the argument goes a large piece of ice from the retreating glaciers was left in the sediment and melted, leaving a lake. Plants grow out from the shoreline of the lake across the top of the water towards the center of the lake. And here is an actual picture of Volo Bog, one of the last quaking bogs left in Illinois. And all you have left in Volo Bog, as far as open water, is that very thing it's not quite in the center there where the arrows are pointing. But the other dark vegetation is actually floating on top of water. The idea is that initially the first plants that grow out over the water are small plants, sedges and reeds, and then as they grow out and build up a soil layer, some taller organisms, taller bushes come in, and as they build up a thicker layer, then taller plants can come in, and so on until we get to a full forest. My experience was I went out with an individual. Bill Maxey was his name. He brought several of us young people out on this expedition. We went into southwestern Michigan, and we got out of the car. We parked along the side of a road in a rural area. No houses anywhere around. We're basically forested area. We got out of the car and went in through the ditch and onto a path through the forest. And we are walking up very steep hills and going down very steep inclines on the other side. These hills were about in the Midwest. This is very steep for us. They were up about 200 feet high, 100 to 200 feet high. They were rather steep. And it turns out, I didn't know it then, but I would learn later, that these are actually forests growing on top of old, ancient sand dunes associated with Lake Michigan. So we went up one sand dune and down another, but we're in the midst of a forest. And there came a point in the path where it became very flat. Our pathway was just as flat as could be, and it was kind of startling. we were huffing and puffing going over these hills, and then all of a sudden, complete flat. We went out about, I'd estimate about a football field, about 300 feet or so into that flat, and Bill stopped us all, and he said, "Okay, now everyone get in a circle and join hands." And I'm thinking, what's going on here? And he says, "Now, what we're going to do is when I tell you to, we're all going to jump up at the same time, and we're basically going to jump up and down. We're going to get into sync. If you get out of sync with everybody else, everybody's got to jump at the same time." Took us a bunch of attempts to try to get to make everyone doing the same thing in the same sequence, like jumping rope or something. But eventually we got into where we were going up and down in the same sequence. And it was at about the time that I realized we were in sync that I realized as I came down that my foot was not hitting the ground at the time I expected it to. That in fact, I fell further than I swore I launched from just a moment before. And as I leapt off of it, it almost felt as if the ground was coming back up. And sure enough, as we were doing this, as we came down, we were deforming the surface of this forest floor. And as I looked around us, we've made a circle. As I looked around us, I could see what looked like a wave in the soil all around us, a concentric circle moving out in all directions away from us, followed by another one as we made another wave, if you wish. And the waves, if you watch the waves, the plants that were standing vertically as a wave would hit would turn, and as the wave went by, they'd go back up again and then come back down and then straighten up. Then the next wave would deform them. So we watched these waves of vegetation deformation go out, and they even came to these large 2-foot diameter trees, and the trees began to sway with this. And I realized all of a sudden that this flat area we were on wasn't soil. in spite of the fact that we're in the midst of a forest of trees, but in fact, we're floating somehow on water, and that we were creating waves in that soil, floating on the water. From there, he took us out towards what would be the center of this bog. We were on a bog. We were on a quaking bog. Quaking. We were quaking it, uh, and as we got further and further out, it was no longer necessary for us to jump up and down as a group. We could do it individually. As we went out further, we realized the trees were getting smaller and shorter, and every step you took moved the surface. And this is when I began to get a little concerned. It's like, how thick is this got to be before you pop through and then you're gone for good, you know? And as we went along, it got to the point where I didn't dare walk bipedally. I got on my hands and knees and walked across, uh, because every movement, and I was just afraid, is going to come right through it. Then it got so bad that, and the plants are now getting really, really short, that I was literally crawling, making sure I was putting as much surface area on the surface as possible to not fall through, until I could actually see at some distance away some open water. And at this point, my face is right in there with the plants, and I'm seeing sundews and sphagnum moss. Oh, it's cool. It's amazing stuff. What an awesome experience. It's If you've not had an experience in a quaking bog, it's really phenomenal. But this is what I thought of when I had come to this point in my research project where I recognized the sequence of plants in the fossil record is very much a water to land sequence, because on a quaking bog we have this sequence from short little sedges and reeds out in the open water, to taller and taller plants, to actually full-size trees farthest from the water towards the shore. And that turns out to be pretty much the order of the in the fossil record. And here's some videos. Hopefully, I took on Volo Bog. So let's see, move forward on that. Here's another one. I'm pressing down on some ferns just to prove that, man, this surface really isn't solid. Here's another one with some cattails pushing down from a floating platform that we're on there. And here's a tree I leaned across, and it's only a few inches in diameter, but there's a tree. I couldn't reach the bigger trees to show those, but sure enough, this surface is unstable or floating. Here's a diagram of a typical quaking bog. It starts on the far left with actually algae and special types of plants that live just underneath the surface, and in fact create a false bottom. It's really interesting. A layer about 6 to 12 inches beneath the surface looks like a bottom surface. So you see a tadpole running around on the crazy thing. But if you put your fingers in, like let's say you're on a boat out there and you reach over, and you easily go right through that vegetation layer. It's really nothing, to really extremely thin. A little further towards the center, or the thickest part of the bog, you have sedges and reeds. Go a little bit further, you get low bushes. You get the low bush cranberries, low bush blueberries. A little further along, there are tall bush cranberries and tall bush blueberries. And then you move into the tree zone when you're farthest away from the water. So again, the idea is the bog is a floating vegetation mat that grows out over the lake. And one thing I remembered from my experience on the bog is that as you're moving from the open water to the forest, the plants are definitely getting bigger, taller as you go along, and the plants are more I'm going to say terrestrial. They have more of those features that allow them to exist independently of standing water. In contrast, the plants of the false bottom have to be underwater, but the plants just landward, if you wish, of those, they are the kinds of plants that actually send sperm and egg in the water. They need standing water. They don't need to be buried in water, but they need standing water at least at some point in the season of a year to reproduce, all the way up to the trees, which can exist independently of standing water. And looking back at that fossil record I was talking about, what we have there, one thing that is quite striking, not necessarily from textbooks because they don't always give our illustrations in with scale, but if you properly evaluate the scale, you realize this Horneophytopsida way down there at the bottom is a tiny little plant. Uh, it's not even as tall as most grasses are, and there's a tendency for us to increase plant size as we go up the fossil record. And as I've already alluded to, the character traits of these plants is increasing terrestriality as you go up. So if we sort of took the fossil record and laid it on its side, so we're looking at the deepest things in the fossil record to the left and the shallowest things in the fossil record on the right. There's a you have and you put those basically underneath a quaking bog model, or putting it another way, if I took those plants that are all the way over to the left, the most water dependent plants, and just projected them straight up on top and said, oh, I think Horneophytopsida is taking the position out there at the edge of this floating mat, and Aglaophyton is right above that, and so on, I can reconstruct a floating forest based upon the order in the fossil record. And that is what is illustrated at the top. It's got progymnosperms out there, those tallest things off to the left, equiseta and lycopods off to the right, and the whole sequence of fossils I'm basically mapping right up onto the floating forest, developing a hypothesis for this thing. And if we assume we're only looking at half of it, if we take a mirror image and put it on the other side and imagine this perhaps in 3 dimensions as a circular phenomenon, so it's got an edge like you see on the left on all sides, and this whole thing not attached to a shoreline, but in fact floating. And the size, given the number of fossils, the distribution of fossils, I would suggest this floating forest is the size of a continent, let's say North America. So we got a floating forest with this composition hypothesized for the pre-flood world. If that was the case, this particular floating forest would probably be quite stable until we got to the flood. But in the flood, we've got a problem because we've got large waves now. As long as the floating forest is staying out to sea between the continents, it's probably still fine. It can be probably deform with large waves. It's really waves that crest that become a problem for something like this. And that would occur where waves impinge upon the continent, where the 3-dimensional waveform as it hits the continent edge gets slowed down as it hits the land underneath, and causes the top of the wave to crest over. That cresting or breaking is the kind of thing that would mess up a forest like this. So if in the course of the flood, the waters would rise up to such a point where the forest would begin to float over the continents, now being submerged, the breaking waves would begin to break the floating forest up and would drop pieces of it from the outer edge first all the way up the sequence, the first things buried would be the things on the outer edge, and then gradually you'd be burying things further and further in towards the center of it. And so we could produce, in the destructive nature of the flood over the continents, the distribution of plants that we see in the fossil record. So what's interesting about this, back up a little bit, if we were on this pre-flood floating forest, and we're out there at the left edge, looking out to looking at what it looked like. What would it look like? Well, if you go into a museum and they show you a diorama of what the fossils look like, what the forests look like in the Devonian, where the Horneophytopsida and so on, their dioramas, their reconstructions of the Devonian would actually be a picture of the edge of the floating forest. If you ignored, for example, those mountains in the background and just saw ocean as far as you could see out, this would be what the floating forest looked like on its outermost edge, the flood. The early Devonian landscape, or the lower Devonian landscape, would actually be the edge of this floating forest. Then the Carboniferous reconstructions, the coal forest reconstructions, would in fact be the center of this floating forest. The beautiful dioramas, such as the one on the lower right in the Field Museum of Natural History, spectacular three-dimensional, full-size diorama, would be a picture of what this floating forest looked like in place. So the large dragonfly organisms and so on. So that's the center of this floating forest. This concept of a floating forest destroyed in the flood would explain several things that we see in the fossil record of the plants. It would explain the increase in size that we see in Paleozoic plants. It would also explain the increase in terrestriality, that order that I was talking about of the major groups of plants. But it doesn't stop there. The cool thing about this theory, and why I say it's the kind of theory we should be looking for, is the theory actually explained far more than it was designed to explain. Let me be clear here, because people have criticized this theory and said, oh, he's trying to explain the coal seams and all of that. I told you, you have heard from me what prompted me to come up with this hypothesis. It had nothing to do with coal. I was not trying to explain coal. I was not trying to explain the Carboniferous. I was not trying to explain even the increase in size or the terrestriality. I was trying to explain the order of the plants in the fossil record, of which the coal plants are only a small part of the story. It's the fossil record order I was trying to explain, not these other things. But once the theory had been laid out, and once I began examining the implications of the theory, I realized that it explained far more than what I created it to explain. For example, the interesting thing about these plants, you saw a bunch of words out there you probably had never heard of: Aglaophyton, Horneophyton, Rhiniopsida, and so on and so forth. Well, why haven't you heard of these things? Well, it's because they're almost all extinct. All of the lower ones are definitely extinct, and there's only a few representatives of the thousands of species of some of these other groups that are there. So all these plants are largely not with us today. One thing that's about this theory is that if we did have a floating, continent-sized floating forest before the flood, it could never have regenerated itself after the flood. God could have created a forest like that on the ocean, and it would have been quite stable on the ocean, staying out to sea. But once the flood had occurred and it was destroyed, the oceans are too unstable to ever allow anything like this to recur. So all the plants that would have existed on this floating forest would have had to fend for themselves on the land. They would have had to compete with plants that were designed for the land, and they're not likely to fare too well in the post-flood world. And so I think the floating forest not only explains the fossil record of these plants, but also explains why it is the plants are largely extinct. Most of them are completely extinct, and other groups have only a few organisms left in the once large groups. Also, another observation is that all of the early plants, all of them, are found in marine sediments or sediments that are interpreted to be marine sediments. And I remember distinctly this being explained in paleobotany as plants living next to creeks or whatever, and the creeks carry the plant parts which float down to the ocean, and they get buried and preserved there in the ocean. So all the early plants, they're supposed to be land plants, but they're not found in land sediments. They're found invariably in marine rocks, the very earliest ones. And that always seemed puzzling to me, why it is that the plants were only, at least initially, preserved in marine sediments. But this would explain why, because they they're basically a marine environment. Yes, they created a terrestrial environment that wasn't part of the marine realm, but they were floating in the marine realm. So technically, they're part of their marine environment, and they were destroyed in the midst of marine sedimentation in the flood. There's another thing that I did not realize at the time that I was creating the initial theory, but discovered later. Many people have accused me of lying here, that actually I knew about this before, but I honestly didn't know about this. There was a theory that had been generated in 1981 by Joachim Scheven, pointing out the strange nature of the plants of the coal seams. Now, none of these earlier plants, none of the plants that I was most interested in, these are specifically plants in the Carboniferous. And some things that are really cool and weird about these things is that they're hollow. Now, I've been criticized for saying that they're hollow because, true, they're not technically hollow when they were alive. But I've seen a lot of fossils of these crazy things, and all the fossils are hollow because, from what we can deduce, the structures that did exist in the center were soft tissue, and they're called erynchymus or air tissues because, in fact, they're designed to transmit air from the atmosphere into the root structures. And I can get back to that. The the structures, they actually do have tissues in there, but they're soft tissues with a lot of air. They're actually purposely storing air. So yes, technically they're not hollow. I'm sorry for the confusion in saying that they're hollow structures, but for all practical purposes they are, and very quickly they get they decay out. We find many of these things full of sand on the inside. Rarely do we find them. Sometimes we find them collapsed, and most of the time we find them filled with sediment. I've never seen one preserved well enough to see the soft parts. So that's why I always understood them to be hollow. Technically, they're not, but I'll call them hollow for our purposes here. What's interesting about these is not just one type of plant, but just about all the types of plants are hollow. With hollow, they're not roots, they're called rhizoids, but these root-like structures, these structures that look like roots, they're also hollow. So the stem is hollow, the root-like structures are hollow, the branches are hollow, the whole thing is carrying air. And the argument is, or what we now believe is true, and I didn't understand it back 40 years ago or whatever, 30 years ago, is that especially in environments where there's not a lot of oxygen in the water, and in situations where the plants are actually photosynthetic in their underwater structures, in these things that look like roots. They're not roots. They're actually underwater photosynthetic structures that need carbon dioxide uh, to do photosynthesis. There isn't enough carbon dioxide. I said oxygen. Sorry, mistake. There isn't enough carbon dioxide dissolved in the water to supply the carbon dioxide necessary for the photosynthesis. So the plant actually conducts carbon dioxide from the air into the roots, the backwards kind of thing, to supply for photosynthesis in the roots, suggesting that these roots, first of all, are not in they're not in soil, they're in water. They in order to utilize light from the sun, they can't be in soil. But not only what was pointed out by Joachim Scheven was not that uh, so much. He didn't understand what the erynchymus tissue was actually doing, what its purpose was. But it was odd that to him that these structures were in fact hollow, and that the rootlets on these root-like structures left the roots at 90 degrees to the root, so they didn't branch out. They actually came out perpendicularly to it, about the size and shape of a soda straw, uh, and in spiral fashion around the root. Uh, Very soft. When you find these things in the fossil record, it's very clear the structures are soft. They're not tough. And the question is that Joachim Scheven asked is how in the world could such structures grow in soil? How could hollow roots grow through the soil without collapsing? How could these soft uh, perpendicular structures, rootlet structures, go through soil? And so he argued that the anatomy of these plants argued that they were actually not in soil, but in water. And so he argued that the trees that are found composing the coal are actually from floating forests, floating trees. Now, he didn't postulate the kind of floating forest I'm talking about, which is much more extensive and involves many other things than just the coal plants. He's just talking about the center of this thing. But based on just the anatomy of these plants, he argued that these were floating plants. And that is therefore, the anatomy of these plants is independent verification of the claims of this theory. In addition, what I referred to as what we now understand about the erynchymus tissue that suggests that these are photosynthetic appendices is further confirmation of the floating forest hypothesis. But then there is the coal issue, because in fact, it wasn't designed for the purpose of explaining coal, but it easily fit in with Steve Austin's coal formation theory that he developed for his dissertation in 1979. According to conventional wisdom, coal is formed in swamps. Vegetable material falls off of the trees that are growing in swamps and accumulates there at the bottom of the swamp. But the problem is that coal seams, when they're found, have several features that are hard to explain from a coal swamp theory. These things often have very flat tops. They have very flat bases, and they sometimes have thin layers of clay that separate two layers of coal, called benches. And these can be just even a fraction of an inch thick and be traced across counties. This is what Steve Austin observed in the Kentucky 12 coal in western Kentucky. Extensive over counties, he saw this strange characteristic. But how do you get a coal forest to, let's say, at the end of deposition, it creates a flat top coal? I was told when I was in school that that's because a hurricane came through all the forest, and I was from Illinois. I didn't experience hurricanes, so I bought it. It's like, okay, until I saw my first hurricane in South, and I saw a place where a swampy area near the beach was hit by a hurricane. One thing that hurricane did not do is level that place off flat. I mean, there were plants going all over the place. It was a mess. You couldn't walk through it. So how do you get a flat top at the end of deposition? And that's actually the easier part to explain, because how do you get the flat bottom? If these are plants that are growing roots into soil underneath, the the plant material should be continuous with that material underneath, should have roots that go from the coal into the shale underneath. But that's not what you find. You find these very flat bases with no connection to roots underneath. You'll have fragments of roots underneath, but you don't find any connection with roots underneath. And you have a flat top. And then the worst part is try to explain a bench. Let's say we could take a lawnmower and shave off the forest. And okay, then we have some mud come in. So we got 3/8 of an inch of mud or something. Now try to regrow a forest on top of that without disturbing that 3/8 of an inch of mud. You can't do it. There's just no way. So Steve looks at these characteristics of the Western 12 coal, or the Kentucky 12 coal seam, and says, how do we explain it? And they're also made of the bark. The coal itself is made of chunks of bark. Steve is pictured here in one of his less conservative days, in terms of clothing, looking at a drain coal swamp or drain swamp in Nova Scotia. And we have the black plant material that could form into coal in theory, but running through it, what do you see? Those white things sticking out are roots. Makes sense. So you wouldn't expect the coal to be made of recognizable pieces of bark. You would expect that stuff to have been decayed away and broken up by the roots. And you would expect roots in there, not bark. So that what we knew about coal swamps just didn't what is seen in coal seams. So Steve Austin came up with an idea that in fact floating logs, not a floating forest, floating logs. He clarified to me years ago that my floating forest thing had nothing to do with his floating log. He has these hollow logs floating around, rolling up against one another, peeling off the bark as they roll, and the bark falling down to the bottom of the body of water that the floating logs are floating on. And as the wind blows the floating log mat along, it drops this bark peat underneath it. And of course, it could easily do this on a flat surface, so create a flat base. And as long as the log mat was over the top of it, it would accumulate more and more coal, or vegetable material that's going to become coal. Then the wind can blow it away for a while. Mud can come in, create that bench. Then the log mat can float in back again and continue with deposition on a flat surface and end with a flat surface as it floated away. It's a beautiful explanation for the origin of coal. And it was even potentially verified by, very soon after his theory in 1971, Mount St. Helens blew its top, and he couldn't resist but to go down into Spirit Lake to see what was down there, because on the surface you have logs that have rolled up against one another and peeled off their bark. Going down at depth, he finds a layer of bark at the bottom of Spirit Lake that seems to confirm at least some aspects of the reasonableness of his theory. So I think he's got a very nice theory for the explanation of coal. It explains also why, if you follow the coal laterally, the coal will grade into marine sediments because it's in a marine situation. It's also consistent with the fact that we have C14, measurable amounts of C14 in the coal, because it was only deposited at the time of the flood, not so long ago. The biomass involved is the biomass of the coal is what you might expect from a continent-sized floating forest. The and if in fact this was a global flood, and it was a continent-sized forest that has now by this point in this system been completely destroyed, and all you have left are logs. The forest itself is gone. All left are the floating logs. That that huge mat would be blown over a continent-sized area, explaining the distribution of coal from Missouri to into Russia. It also explains why the the coal to sandstone to limestone sequence is repeated over and over and over again, because every time the log mat gets blown over an area, it would repeat that sequence. It also explains why, if you look at just the Carboniferous, just the sediments of the which is lots of sediments of the Carboniferous, you find the same critters and the same plants all the way up through the section. It's not 100 million years of time. It's all in one flood event. So I believe the floating forest theory explains those things. Plus, another thing that I realized towards the end of this was that if there are specially designed organisms to live in various parts of this bog, it would explain their distribution as well. If God designed an organism that could live in that soft area at the end of the bog where I couldn't crawl out to, because I couldn't do it as a biped for sure, I had to be quadrupedal, but even then I could get out further, I would still fall through. So an optimally designed organism might be one that can float in water and have something like legs that move around on the bottom underwater. So a fish pteropod, a fish with legs, would be specially designed for this portion of the sequence. Then we have, as we move inward, we got organisms designed. You four-legged organisms like large amphibians could live in the soft areas, but not really soft areas. And then, of course, full reptiles and so on in further. And that as the flood deposited the plants in a particular order, it would also deposit these organisms, these animals that are associated with it in the same order. This would explain the apparent transition in the fossil record between fish and fishopods and amphibians and reptiles that is found in the same sediments. So I believe the floating forest theory explains a number of things we see in the fossil record. It explains the increase in plant size, the increase in terrestriality, the fact that Paleozoic plants are near extinct, the intermediates of these animals along the edge of the coals of the floating forest. It explains why we have these plants in marine rocks, why the Carboniferous trees are hollow, why we have the perpendicular rootlets, why we have flat top, flat base coal seams, why we have coal made of bark and coal benches. It also is synthetic. It brought in Steve Austin's log mat model. Yes, he didn't postulate a forest growing in place, but once you destroy that forest, you now have the log mat that Steve needs to generate the coal. It also pulled in Joachim Cheven's floating forest theory, so it's a synthetic model, and it's heuristic. It's able to engender new research, looking at things in a different way and different tests. I think one thing that's another interesting thing that's come about is we've learned that some of these plants, actually their seeds, they have these mega seeds that are actually little boats. They float around on the surface of the water and they generate roots while floating, which seems to put them into that category of floating plants in general. So this is the kind of theory in general that we want in creationism as we build our model. We want theories that explain data that we know about, explain data we didn't know about till we saw the hypothesis, and bring in or synthesize other theories that already exist and pull them in and suggest future research and future testing. These are the kind of theories we should have in creationism, and it's an example of one of actually a number of theories that we now do have in creationism that are of the sort that we desire. So thank you very much.